This is the second part of the module on internal forced convection. Previously, we looked into the hydrodynamic and thermal entry lengths, beyond which we have fully developed flow hydrodynamically and thermally. Basically, the flow in a channel is divided into these two regions, developing region and fully developed region, thermally and hydrodynamically. Now, the length of the entrance region may be determined with this approximation if the flow is laminar. That means the entrance length hydrodynamically is 0.05 multiplied by the Reynolds number multiplied by the hydraulic diameter. And the thermal entrance length is just the hydrodynamic entrance length multiplied by the Prandtl number. For turbulent flow, the hydrodynamic and thermal entrance length is approximately the same. It's equal to 10 times the diameter of the channel. So again, the critical Reynolds number is based on the hydraulic diameter, and turbulence starts to occur when Reynolds number is 2300. This is a bounded flow. The critical Reynolds number occurs early. Next, we go into general thermal analysis. If you remember, we have two boundary conditions, the constant temperature boundary condition and the constant surface heat flux boundary condition. Let's have a look at the constant surface heat flux first. For steady state conditions, no thermal energy generation, we have an energy balance performed on the section of the channel. So we have the energy brought in by the mass coming in and leaving equal to the heat gain from the constant heat flux. Yeah. If we rearrange H16, the fluid temperature at the exit may be determined. Because we know the heat flux, we generally want to know the exit temperature and the surface temperature. So the exit temperature may be obtained by rearranging the H16 and you get H17. Here, knowing that the heat flux is constant, the inlet temperature is known. Generally for steady state, steady flow system, mass flow rate is constant, and so is specific heat at constant pressure. So H17, if you look at H17, can you see that actually the exit temperature is increasing linearly with x being the distance to the right. See? Can you see why? The surface temperature for constant surface heat flux may be determined from the Newton's law of cooling. As here, that is, if you know the average heat transfer coefficient and the mean temperature along the channel, which we'll go into later. Okay, so for a fully developed flow region with a constant average heat transfer coefficient, the surface temperature increases linearly in the flow direction. We assume constant thermophysical properties. Yes. So with Qs constant, the average heat transfer coefficient constant, with mean temperature increasing linearly with x, so will the surface temperature. So the difference here is constant along the channel length. Now, since the flow in the tube is fully enclosed, an energy balance may be applied to determine how the mean temperature varies with position along the tube. So you have an energy balance, the energy brought in by the mass flow into the infinitesimal small control volume, and also energy brought in by the constant surface heat flux via convection, and energy left brought out by the mass flow out of the control volume. So you have an energy balance here, which finalized into this equation. The change in kinetic energy and potential energy are neglected. Now, the rate of convective heat transfer for a differential control volume may be written here. Perimeter P is just pi d for a circular tube. And upon rearrangement, we get 819. Now, note that since the surface heat flux is constant, perimeter is constant, mass flow rate is constant, and we assume constant thermophysical properties. So this whole thing, the rate of change of the mean temperature along the channel length is constant. So integrating 819, yes, integrating 819 from inlet to any location X along the channel, we get 823, where you can see here the mean temperature varies linearly with X for the total length. So if the length is L, so it depends on AS, it's a surface area, which depends on also on the location. How long is the channel length that you are performing your heat transfer analysis. Note that surface area and cross-sectional area are different from each other. Okay. So this is for the temperature profile for constant surface heat flux. Notice that Ts minus Tm is constant after the fully developed, in the fully developed region. There's constant surface temperature, they are not. The second case is a boundary condition, constant surface temperature. We look at the heat transfer now. Because we know the temperature, surface temperature, we would like to know the heat transfer rate to or from the fluid flowing in a tube. So we use Newton's law of cooling. So we have 825. Okay. Here, the delta T average is actually some appropriate average temperature difference between the fluid and surface, which is generally taken as surface temperature minus bulk temperature. The bulk temperature, T subscript B, is the average of inlet and exit of the channel. Now, for constant surface temperature, the arithmetic mean temperature difference is given by this equation, which is surface temperature minus the bulk temperature. Now, 826 is not a good approximation to represent delta T average. What is a good approximation? Well, let's have a look. Now, knowing that the fluid mean temperature increases linearly along the tube from an energy balance, so we have the energy brought in by the mass flow rate equal to the by the heat flux, by the heat coming in from through the channel wall. We have 827, which upon rearrangement, we get 828. Now, noting Ts is a constant, so we take that, separate the variables and integrate from the tube inlet to exit. Note that delta Te is actually surface temperature, which is constant in this case, minus the temperature at the exit. And delta Ti is the surface temperature minus the temperature at the inlet, the mean temperature at the inlet. When we integrate, we get the logarithmic solution form. And knowing that here, the H is the average convection heat transfer coefficient, it may be simplified to get 829. Now you rearrange at 29 for a channel length L, you will get this equation. Remember again, Ts is constant. This is a boundary condition where surface temperature is constant. If the integration is done over a distance x from the inlet, we would have obtained a more general expression, given by 830. And this quantity, average heat transfer coefficient multiplied by the surface area divided by the mass flow rate multiplied by the specific heat capacity, is called the number of heat transfer units, NTU, which is a measure of the effectiveness of the heat transfer systems. Now, look at equation 830, you see that actually the difference between the surface temperature and the mean temperature decays exponentially with x. Right, it decays, it's decreasing exponentially. So knowing the surface temperature, so we said earlier, we want to know the total heat transfer rate for flow in a pipe or channel with constant surface temperature on the walls. We have here, remember the earlier equation, rearranging, we get, and substituting the m dot Cp from 831, we get what we finally is interested in, which is 832. So this is for the boundary condition of constant surface temperature. The heat transfer is equal to the convective heat transfer coefficient, average, multiplied by the surface area, which is pi d, d being the diameter of your circular channel, and the logarithmic temperature difference. This is a form of Newton's law of cooling for the entire tube, and delta T logarithm is the appropriate average of the temperature difference over the tube length. Okay, it's defined by 833. So this is a better delta T compared to the arithmetic mean. Now, in many applications, it is the temperature of the external fluid, ambient temperature, that is given rather than the tube surface temperature that is fixed. So in this case, when the surface temperature is not given, the ambient temperature may be used instead, and the average heat transfer, convective heat transfer coefficient, is replaced by the overall heat transfer coefficient. Remember chapter 3 of your ebook? Yes, so you may replace that and you get this equation. Now note that the average U takes into consideration the convection from inner and outer surfaces of the tube, as well as conduction, if there is any. The thickness of the channel is given. So finally you get this equation. Remember R total from 319? Okay, so this is a general thermal analysis for two boundary condition types, the constant surface heat flux and the constant temperature on the channel wall. How to get the H? We'll see that in part 3 of this module.